Hello, everyone. I'm Joe Pryweller, Senior Director of Conference Content for Rubber News. I want to welcome you to this webinar presented by Alpha Technologies and hosted by Rubber News. This webinar will outline the FT-Rheology LAOS test method and how to use it in a rubber process analyzer. We'll provide you with case studies that help you to better understand the data and results from the LAOS method. Today's presenter is Rick Hanslick, Product Manager for Alpha Technologies. Rick has more than 10 years of experience in the polymer industry with over 15 publications on elastomer testing. He is Alpha's resident in-house rheology and testing expert with over 5 years of experience using Alpha instruments to solve customer issues. During the course of the webinar, you can ask questions opening the Q&A icon located at the bottom or the top of your computer screen, and then typing in your question. Your question will be asked in the order that it is received. After the presentation portion, the webinar is completed. At this point, let me turn the presentation over to Rick Hanslick of Alpha Technologies. Rick, the floor is yours.
Thank you, Joe. So today we're going to be talking about LAOS. So a little bit of background on the agenda. We want to understand what are some of the common processing problems, give a brief introduction to LAOS or Fourier transform rheology, and then run through a number of case studies. So we're going to look at understanding the effects of additives, in this case a PVD, solving extrusion challenges on an EPDM material, effect of synthesis methods on SBR, evaluation of melt fracture on a polyethylene, and gel detection with a BR and an NBR. So the problem: polymer architecture can have a large impact on the processability of rubber materials. Processability means how well is this material going to mix, extrude, mold, basically how easy is it to process or make it do something that you want it to do. Unfortunately, traditional rubber QC test methods lack the sensitivity to make assumptions about polymer architecture, such as molecular weight distribution, branching, or the presence of gel. On the other hand, more advanced laboratory techniques like gel permutation chromatography or GPC that can provide this information are often expensive, time-consuming, and require a highly skilled operator or chemist to perform the tests. Therefore, the introduction of a quick, easy-to-perform, and sensitive technique to quantify polymer microstructures can help avoid product failure and costly scrap material. So, the current state of QC in the rubber industry. Today, the quality control test in the rubber industry is done mainly by 4 different test methods, such as the density of the cured rubber, the hardness of the cured rubber, the cure curve, or like an MDR or ODR curve, and Mooney viscosity. Some limits of these approach are, a lot of these are labor intensive and not advanced enough to recognize the main difference between the examined batches to predict the processability and the final properties of the cured compound. So when we're looking at hardness testing or the durometer testing, essentially we're applying a load and we're seeing, we're quantifying the indentation of that material. So the complex deformation gives us a stress response that's not terribly well defined. And there's different types of hardness testers. You have type A, type D, Shore A, etc. And then for curing curves, this is done in quality control, typically a very rapid 3-minute at high temperature, only to check if the compound curatives are added. So this is really just a quick and dirty test to make sure that the ingredients that are supposed to be in the rubber actually are. It's not going to give you any advanced information. And then Mooney viscometer is kind of a staple of the rubber industry. This is kind of, again, a quick and dirty test to look at processability. Typically, you'll run a ML1+4 or ML1+8, which is 4-minute, or technically a 5-minute test or a 9-minute test, where we're just measuring viscosity of the last 30 seconds of that time frame. And that gives us a rough idea of how easy is that rubber going to be to process in terms of Mooney units. However, you do, as you can see in the drawing here, you can run into some edge effects as that rubber starts to cure up, as that flow starts to become more difficult. And so this is actually introducing variation and error into the measurement system. So next, we're going to talk about just a brief introduction to what is LAOS, or Large Amplitude Oscillatory Shear. That's what LAOS stands for. How does it work? How does Fourier transform and harmonic analysis play a role in this? And do we have to do all this math? And I can answer the last one quickly. The answer is no. So the Fourier transform rheology via LAOS is probably one of the most sensitive test methods to characterize nonlinear response of viscoelastic materials in a shear or viscometric flow, and is probably the best way to quantify the level of LCB, or long chain branching, in polymers. And this test is kind of SSW, or more in general, an MX test, subtest, or matrix subtest. And essentially what we're doing is we're applying a very large strain, typically 500% strain, 1000% strain, 1200% strain in some cases. And we're using a software module that records the first non-odd higher harmonics of the torque signal, and then evaluating those differences in signal against one another. So the most common analysis approach or techniques used to apply the LAOS characterization is to use Fourier transform rheology, or like we called FT-Rheology. The FT-Rheology technique was developed several years ago by Deely and Giacomin in 1992 to characterize the nonlinear viscoelastic behavior of complex fluids, mainly soft polymers. Based on this theory, the stress signal can be described in the nonlinear regime as a Fourier series, which is the sum of all of the higher harmonics of G prime and G double prime. And we use the odd harmonics because typically polymers respond as a square wave, or yes, a square wave. And so we need to focus in on those odd harmonics as opposed to the even harmonics, which provide a triangle wave. So with this approach, we only have two terms, like in the linear viscoelasticity. Alpha was one of the first companies to introduce this feature on the RPA, or rubber process analyzer. So to explain the main difference between the linear and the nonlinear viscoelastic regime or region, we would like to clarify what this point means. And so we have to talk about linear viscoelasticity. And essentially, as we see on the chart here, the area of linear viscoelasticity is, as we increase our strain angle, it produces a linear or flat response from the polymer. So we see on the left-hand side, where we're increasing strain up to about 50%. Up until this point, our modulus response of the material is flat. So this is called the linear viscoelastic region. And where we start to see that strain softening characteristic outside of the linear viscoelastic region, that gives us the non-linear viscoelastic region. Typically, this area is not going to change too much in response to frequency. However, it will respond more to strain. And when we get into the Fourier transform analysis, we kind of look more at shear rate, but we'll get to that in a second. So in the non-linear viscoelastic region of the shear stress signal, it is no longer an ideal sine wave. And so the way the RPA works is we apply a sine wave, a mechanical sine wave to the material, and we record its response to that deformation. At low strain, or low signal, or low shear rate, typically that response is perfectly sinusoidal, the mechanical response. When we get to these high strains, or these high shear rates, we can see a deformation in that signal. And so this is because the signal becomes distorted, and the higher this distortion is compared to the trends of the linear viscoelastic region versus the nonlinear viscoelastic region, will tell you characteristics about some of that polymer architecture. And we can look at things like whether or not the deformation is leading or lagging. So for example, when we look at 1000% strain, T is not that sine wave, and the distortion is very pronounced. In the next slide, I'm going to clarify this point a little bit more to show the contribution of each odd harmonic component of the torque. So here we're looking at the first harmonic of the torque, which is the fundamental torque. And this is measured by all RPAs without applying the Fourier transform analysis. As you can see here, using only the first harmonic composition is not possible to detect any distortion of the torque signal. So if you're just running a normal strain sweep, a normal RPA measurement, this is typically the response that we're used to. However, when we start to break down into this harmonic analysis, we see here the third harmonic, and this is the one that occurs obviously after the first. And we can see that the distortion we don't see that in each individual harmonic. It's when we put them all together that we can see that distortion. So we started with the first harmonic, then we get to the third harmonic. We see that the signal from the third is slightly less than the first. Then we move to the fifth harmonic. The trend continues. The seventh harmonic. So as you can see from these trends, the intensity of the odd harmonic contribution decreases significantly as we go from 1 through 9. And then by adding all of the odd higher harmonics of the torque, the first, third, fifth, seventh, and ninth, you can get the real torque signal of your material when you apply the high strain. As you can see in this case, the distortion is very pronounced and the real torque deviates significantly from the ideal sine wave. The first harmonic, and we see that in the first harmonic. Therefore, the Fourier transform rheology is a powerful tool to quantify the distortion and probably the best way to study the polymer architecture and quantify the level of LCB or long chain branching in polymers. And so depending on if that distortion is leading or lagging can give us information of if we have a highly branched or if we have a linear polymeric structure. So the FT-Rheology via large amplitude oscillatory shear, LAOS as we've been calling it, is recognized as a very sensitive technique for detecting the LCB, or more generally to distinguish between different polymer topologies. As you probably know, the presence of long chain branching in a polymer has a large impact on the viscoelastic properties and can significantly influence the processability of rubber compounds. And even filled rubber compounds, for example, black incorporation time, dye swell, extrusion behavior. LAOS responses can be described or visualized as parametric curves called Lissajous plots. And these figures are the oscillating shear stress versus strain over time, demonstrated by an experimental work developed at the University of Louvain, that with this graphical representation, it is possible to distinguish between linear and branched polymers. In fact, only polymers characterized by a completely linearly show these additional secondary loops. So we can see on these plots, we have Lissajous plots with no loops, and we have plots with loops. So in the case that we have the loops present, those would mean a linear polymer. When we see no loops present, then we know that it's a branched polymer. And then we can look at the width of that center point. And as that width increases or that breadth increases, we know that our LCB, or long chain branching, our degree of long chain branching, is also increasing. So basically here we're looking at a short mathematical outline followed to determine the analytical conditions associated with the onset of these additional loops. So here's essentially the math behind what these Lissajous plots are showing. So in this case, we're looking at E3 is going to be equal to some constants where we're looking at G prime at the third harmonic divided by G prime at the fifth harmonic minus G prime at the third harmonic divided by G prime at the fifth harmonic. And so we can follow these mathematical assumptions to essentially create an index for long chain branching. And per this index, as our value increases positively, we know that it's becoming more and more branched. And as the value decreases, it's becoming more linear. So these are some of the schemes of possible long chain branching that can be detected by the methods that we just talked about. So we've got some different geometries that it can occur in terms of that long chain branching. So long chain branching greatly complicates the characterization and description of the molecular structure. It is possible by other methods to prepare samples having reasonably uniform branching structures, such as stars and combs, but long chain branched commercial polymers are usually randomly branched and may have complex structures in which there are distributions of backbone lengths, branch point locations, and branching complexity. So essentially what we're saying is where the branches occur, how big the branches are, how many branches there are, all of these things are going to affect the processability of your polymer. And if they're random, every time you synthesize a new batch of polymer, these things, these characteristics can change. So we want to be able to create, obviously, consistent batches over and over again. So we need to have a testing instrument that's sensitive enough to be able to detect these differences from batch to batch. So even the identification of a backbone is problematic when there are branches on top of the branches. So you can actually get branches on top of your long chain branches. For example, low density polyethylene made by high pressure via a free radical process is an example of an important commercial material with very complex branching structure. So now we're going to jump into some case studies which apply these mathematical models, the LAOS test method, and the Fourier transform analysis. So here we're going to look at a couple different materials, EPDM, NBR, SBR, and some polyethylene. So in case one, we're going to try and understand the effects of a coupling agent on a polybutadiene, or PBD. So in this case, we had 3 different PBD samples, A, B, and C, with different coupling agent contents. So we're looking at millimoles versus mole of the initiator. So they're basically the ratio. So we did a 1.8, a 2, and a 2 and a 5. We see the effects on the molecular weight. We see the effects on the ml 1+4. So on the scheme of things, not particularly different from one another. But when we look at the LAOS plots, it will be a little bit more informative. So by comparing the Lezage figures of the investigating samples, it was possible to detect the increase in the long chain branching content from sample A to sample C. The higher the level of the LCB, the more deviation from the loading part of the stress signal from the unloading part, thus increasing the loop surface and balancing the distortion. So we see here sample C shows a significantly different plots from sample A and B. So using both LCB indexes that we mentioned before, so we've got LCB index 1 and LCB index 2, which is a little bit more of the complicated equations. We look at sample A with an LCB index of 3.85, sample B with an LCB index of 4.88, sample C with an LCB index of 6.61. And from this, it's possible to quantify the different level of long chain branching in the examined PBD samples and confirm the high sensitivity of this test method. The big advantage of this technique compared with traditional rheological techniques, such as the Van Gerp-Palin plot, is that the dampening function by stress relaxation in shear and extensional rheology is that allows to detect subtle variations in the degree of branching due to the different coupling agent content that can significantly affect the processability of the end product. In this case, the examined PD samples are used in the ABS production, are used in ABS production, and a subtle variation in the branching content can cause a worsening of the processability of this material. So if we have too much long chain branching occurring, then that material is likely going to be very difficult to go through the production process. So we want to, in this case, ensure that our LCB index or our long chain branching is sufficiently low to be able to process this material correctly. In the next case, we're going to look at solving EPDM extrusion challenges using our LAOS test method. So in this case, we looked at a Keltan, a Nordel, and a Vistalon type material. And these different grades of EPDM have different molecular architectures and especially a different branching content. Also, in this case, determined by comparing the Lissajous plots, it was possible to detect the different molecular architecture of the examined EPDM samples. Nordell shows a linear macrostructure, while Vistalon is characterized by a branched macrostructure. And then if we were to compare the Vistalon to the Keltan, we would say that the Vistalon has significantly more LCB or long chain branches than the Keltan. And so based off of what I just said, looking at the breadth of that Lissajous plot, we see that the LCB, the calculation of the LCB index confirms this, with the Keltan having a LCB index of 3.63 compared to the Vistalon 7.72. So if we look back, the Vistalon is significantly wider, has a significantly larger LCB index, while the Nordell IP that contains the loops that we discussed, we see has a negative LCB index, which indicates that it is actually a linear polymer. So this approach can be used for quality control in the synthetic rubber production to check the polymer architecture. In this case, the LCB index of an EPDM grade is monitored, tracked during the production run to check the branching or LCB content in different lots. And we can see from the figure here, the same approach can be used by compounders to check the quality of raw materials or elastomers. So that would be incoming batch validation. So when you get your truckloads of raw materials, you can actually run them right on the RPA with this quick LAOS or quick 10-minute LAOS test method, and you can track your LCB content over time. And so typically the LCB in the EPDM grades enhances the shear thinning or flow behavior. Therefore, a lower branching content can cause a worsening in the extrusion process. And then if we look at the chart over time, we can see the different samples and we can see kind of their run history. And we want to make sure that we're not seeing too much variation and that our LCB index is sufficiently high in this case, because we don't want to run into that shear thinning behavior. So in case 3, we want to look at the effect of the synthesis method. So 3 SBRs were polymerized in 3 different ways, resulting in 3 different polymer macrostructures. So in this, we looked at SSBRs. Number 1 is an SSBR synthesized by batch polymerization and is characterized by a linear macrostructure. The second was synthesized by a continuous polymerization and is randomly branched. And the third was an SSBR, and it was synthesized by continuous polymer, synthesized by continuous polymerization, resulting in a star branched, and this is shown by the blue color plot. By comparing the Lissajous plots, it was possible to detect the different macromolecular structures of the examined SBR grades. The batch SBR grade shows a linear macrostructure, while randomly branching is characterized in the other 2. So again, we want to look at the loops, the presence of the loops or not the loops, and we also want to look at the breadth of that center line. So if we look at our LCB index 2, we see that the OE, or the linear SBR, has a negative value. So if we come back here and look at our linear polymer, we see that we do have loops present. So the negative value is in line with what we'd expect. So that's a linear polymer. We've got no branching going on. We've got the OE SSBR with an LCB index of 10.1 or 10.2-ish. So pretty high. So that is the OE SSBR. Randomly branched, so that has a very wide center line. This is giving us a very large LCB. And then we've got the OE star branched, which is slightly less branched, which shows by our 1.2 value compared to the 10. So like we said, when we run into that randomly branching scenario, typically you're going to see much higher LCB indexes because you can have branches on top of branches, very long branches, etc. So the next case we looked at was an evaluation of melt fracture in polyethylene. So in this case, we had two different polyethylenes, polyethylene 1, polyethylene 2. As we know by now, polyethylene 1 is showing clear signs of being more of a linear polymer, while polyethylene 2, lacking the loops, is going to be more highly branched. So we use this to check the presence of the LCB in the polyethylenes and to quantify that content. And then when we come to our LCB index, and one thing that's really nice is that these indices are baked right into the software, so you don't have to plug in these equations that we saw earlier in the slideshow. These are already built right in, and all you have to do is select the data point in your test setup, and it'll spit out this number at the end of the test. So basically, earlier when I asked, are we going to have to do this math? The answer is no. We do it for you. So in this case, we see the minus 3.674. This is in line with our presence of loops. That's going to be a very linear polyethylene. And in with the higher LCB index content of a 4, we know that that's going to be branched. And like we have said, the LCB has a profound effect on the processability of this class of material because the long branches for polyethylenes has been used to delay the onset of melt fracture as we move towards higher shear rates. So depending on what your end application is, it may be necessary to have sufficiently high LCB indices or an LCB index so that you can delay the onset of that melt fracture depending on the process you're doing. In other applications, it might be necessary to have a sufficiently low LCB index. It all depends on the application. So for case number 5, we're going to talk about the detection of gel content. And before we can get into the experimental model for the detection of gel, first we need to explain what gel is. And essentially, gel is areas of very high molecular weight that can strongly impede the processability of a rubber. And so the typical method for detecting gel is to take a sample of material, put it inside of a solution of a solution, and dissolve out that rubber, and any remaining rubber that doesn't go into solution would then be your gel content. So this is a wet chemistry. It's quite time consuming. You have to use the harsh solvents. It is kind of difficult to run. The other method that's commonly used for detecting gel is to cut very thin strips of the material and then use an optical microscope to look for granules of gel present in the material. And this method is very subjective. It can change operator to operator. It's very difficult to create those samples. It's time consuming and manual process. So if we could eliminate both of those methods with, like I said, a quick 10-minute test that just requires a 5-gram sample placed on a die, I think that would be preferable. So in case 5, here we're looking at an experimental BR grade. We have a BR1, BR2 with the same catalyst. They're both cis-1,4s, similar molecular weights, and similar Mooney values. And then we go through a couple different RPA methods that can look at the evaluation of gel content. So the first would be a time sweep at 120 degrees Celsius. So we are evaluating the time response of the material, and we can see that BR2 is going to have a much higher G prime than BR1 as we measure this material over time, in this case, about 1,200 seconds. So the next method that you can also use is looking at frequency sweeps. And so here we're running from 0.1 radians per second up to about 100 radians per second. And we can see that the BR1 is going to have a much higher tan delta than the BR2 at the low frequency response, which is in line. So high tan delta is calculated by G double prime divided by G prime. So as our tan delta goes up, that material is going to become easier to process, likely lacking the presence of gel. And then, of course, we can get into our Lissajous plots. Here we did the BR1 straight out of the production process and 4 days after storage in the oven, so 4 days of heat aging. And we don't see a very large difference between the the Lizéju plots. That center line isn't changing a whole lot. However, on the BR2, after 4 days of heat aging, we see that that gel content starts to increase. And this is in line with what we get from our LCB indices. If we look on the right-hand side, we get the sample BR1, sample BR2. We've got a value of 7, 10.5 compared to 2.1 and 6.3. And then in table 2, looking at BR1 versus BR2 after the heat aging, we see not much of a change on BR1, but on BR2, we do see significant increase in that gel content. So we want to do a correlation between the LCB index and the gel content. So the gel content was established experimentally through other methods, and we can compare the BR2 with an LCB index of 15, and this shows gel content of 17% for that material. For BR1, we saw LCB index much lower of 7.1, actual gel content about 0.2. And so this is just showing that sometimes it's useful to use multiple test methods. So we want to look at the time dependency of the material as well as the LAOS results to get to make some inferences about the LCB index and compared to the real world gel content. So our last case study, which is kind of a continuation of case study number 5, this was detecting gel content in an NBR. So we had 2 samples with very similar ACN content and ML1 plus 4s. We compare sample 1 and 2, looking at that frequency sweep, and we see sample 2 with a much higher tan delta than sample 1. This is kind of an early indicator that yes, this material is probably going to be less branched than sample 1 because we have that higher tan delta. We jump to our Lizéju plot, and we see that, in fact, both of these samples lack our loop. So we know that they're both going to be slightly branched at least. And sample 1, the black line, has a much wider center line of that Lizéju plot. And this, as we know, is going to indicate larger LCB branching. So if we jump back here, sample 2 in the blue, a higher tan delta, probably less branched. Go to the Lizéju plot, and we see that it does have the smaller center line. So we're going to assume when we get to our LCB indices that it's going to be less branched than sample 1. And when we get here, we see that sample 2 does indeed have LCB index of around 13.6 compared to the much larger sample 1 of 17.09. And then lastly, we want to kind of pull it all together to paint the main picture of this. So we did the flow curve looking at the viscosity response to shear rate in radians per second. So we know that sample 2 is going to have less branching, and we see that sample 2 is lower viscosity as we go through that shear rate. So sample 2 is going to be easier to process than sample 1, which has a higher viscosity as we go through that shear rate. So this is kind of making that link that this LCB index can be very useful for predicting the processability of a material and can be implemented into the quality control process and replace some other more time-consuming and very manual measurement techniques that are out there. So to kind of wrap all of these back up, we know that product failure and scrap of material can be reduced by using these advanced techniques such as LAOS. We also talked about a little bit about time sweeps and frequency sweeps. These can be used as well. LAOS, the FT-Rheology, can help you find costly quality problems by giving you a deeper dive into the root of the problem. We know that LAOS can detect subtle differences in the degree of branching due to coupling agents. We know that LAOS can help you check polymer architecture, which can affect your extrusion. We know that we can use LAOS to differentiate SBRs and the different synthesis models that were used, if that's going to give us branch, star branched, linear, etc. And this can help reduce costly scrap as well. In case number 4, the material used in the study helped to detect the onset of melt fracture. In that case, we know that we need a sufficiently high presence of long chain branching to delay the onset of the melt fracture. Again, melt fracture would be very bad in injection molding process. That's going to create scrap or lead to field failures, which is usually really bad. And in case 5, we used the LAOS method to detect the presence of gel, and then compared this to some more analytical methods and found good correlation between the two. So again, that's now taking a several hour test method and baking it down into a quick 10 minutes. And you could probably optimize that to be even quicker test method that you can run quickly on your RPA that's likely already being used in your release protocol. So at this point, I'm going to hand things back over to Joe, and I think we're going to open things up for a little question and answer session.
Great. Thanks, Rick. Terrific presentation. Appreciate all your insights and all the case studies that you shared with everybody today. That was terrific. I wanted to mention that we have a couple other Alpha Technologies experts joining us for the Q&A session. With us today are Michele Sacchi, application scientist, and Yunal Yumazal, applications engineer at Alpha Technologies. They worked a lot on the LAOS testing and some of the technical details surrounding it. So they might be able to answer your questions too, along with Rick. And before we get to questions too, one brief mention. As a reminder, you can click on the Q&A icon located at the bottom of your computer screen and type in your question. Your question will be asked in the order that it is received. So just type in your questions, like I said, the Q&A box located at the bottom and the top of your computer screen, and we'll get to your questions. Rick, let's start with one really general question here. Can you elaborate on the subtlety of the variation detection in your first case study that you mentioned dealing with PBD? You're getting to the right slide there, looks like, right?
Yep, yep. So the subtlety in, are we asking what's the sensitivity?
The subtlety of the variation detection.
I'm not sure I completely understand the question. Basically, I think the question is what's the minimum detectable level?
Yeah, that sounds right.
Okay, so in this case, we see coefficient of variations of less than 1 to 2%. So depending on what the material response is to that coupling agent is going to indicate whether or not this method is going to be able to detect it. So in this case, we see it's a lot more sensitive than some of the other methods that are out there. So in this case, we know that the molecular weights are very, very similar. We know that our dispersity index is very, very similar, 2.2 compared to 2.3. We know that our ML1+4s are very similar, 51, 52, 49. So I'm going to venture to say that this method's a lot more sensitive than what's available currently. So it's going to be able to pick up pretty small differences between these. So if we look at the loading levels, so 1.8 versus 2. So that's kind of giving you an idea of what that minimum detectable level is. Minimum detectable level meaning what's the smallest amount we can change the formulation and be able to recognize it through our testing. So in this case, a 0.2 millimole versus mole of initiator is able to be detected in this particular case.
Okay, terrific. Question from one of our participants. Do you visualize non-contact type rheology measurement systems in the near future?
Non-contact type rheology systems.
Yeah.
Michele, are you on the call? I'm not sure. I'm not quite familiar with non-contact rheology.
To be honest, I'm not familiar with this nomenclature. If you can specify this type of technique, probably, but I'm not familiar. Sorry.
Okay. Well, if the attendee wants to, type another question in the chat that might be more specific, maybe we can answer that. But right now, we'll leave that one alone. Another question: do you think it's possible to determine a certain rubber's viscosity at nonlinear viscoelastic conditions, such as during injection molding?
So we, as shown by Rick in the presentation, probably in the last case study, so we can, because the long chain branching indexes that we obtained by using this approach can be well correlated with the viscosity or the flow curve that we obtained by performing frequency sweep tests. So this it was confirmed. So not only for injection, but for several type of processes, extrusion, and other processes in which we can generate the flow curves.
Okay, thanks, Michele. Case study number one, again, a question again about that with using PBD and compounding agents, coupling agents, excuse me. You show that Mooney viscosity, no distinction versus the LAOS plot. Would Mooney SR have shown any deltas with this?
So the Mooney, in this case, Mooney stress relaxation is the additional let's say test that was mentioned in the. So the Mooney after the standard Mooney test, the Mooney relaxation test cannot provide additional information. We have checked, of course. And as mentioned by Rick, since the coupling content in the different samples that we have examined are really less, so very small, the variation, we didn't find any additional technique that was so sensitive to, let's say, to determine the branching content.
Okay, great. Another question here. Could we use LAOS to evaluate the variation in mixing using the same polymer?
For the mixing, of course, branching has an influence, as we mentioned several times. For the mixing, we, let's say, we create, let's say, another test method that was not shown in the presentation. Probably we can, so in the future we can provide also a slide deck for this topic. So for mixing, we have created a specific test method that can be used to determine the filler dispersion. So it's very useful for mixing.
Okay, terrific. Thanks, Michele. Can you characterize what you're talking about with bimodal structures? Which just give a little definition of that, I guess.
Can you
characterize it? I guess bimodal structures.
Bimodal, okay. Bimodal, of course, because most of the let's say polymer that we show in the presentation, we consider in this study, are bimodal with a bimodal distribution. So it's very useful specifically for industrial polymer that are bimodal. Yeah.
Okay. For industrial polymers, you say that are bimodal.
Yeah.
Okay.
Yeah.
Okay, great. Can the LAOS method be used to compare polymers outside of the branching? And are there any examples on fluoroelastomers, for instance?
So for fluoroelastomer, we use also we have not displayed an additional case study for fluoroelastomer, but we have also used for the branching content. It was also useful, but is focused mainly on the branching, not on let's say, to disclose all information of the macrostructure. We combined the LAOS technique that we are talking on with the typical linear viscoelastic characterization. So by performing frequency sweep test at different temperature. and we combine all information.
Okay.
But,
So
yeah.
Go ahead.
No. Is so LAOS we should be used in the let's say in the way that we described today, and we combine with this technique, the LAOS technique, with so the frequency sweep test that we perform in the linear viscoelastic region.
Okay. Great. Okay. So but now with fluoroelastomers, there's still some work to be done with that. Haven't been tested yet, right? With that.
Mm-hmm. Yeah.
Okay. Excellent. How do you determine the test temperatures and the frequency for getting the maximum sensitivity on the LAOS test?
So typically is based on the experience, but if you don't know let's say any information about the polymer that you are characterizing, you can perform, for example, the time test, time sweep test that was also shown by Rick. We look at the let's say the trend of G prime versus time. And in case so at different temperature, of course, we perform this test. And if we, let's say, we detect that the slope of this curve is sharp, then it means the material is probably not stable at this temperature. So we can use this plot to determine the maximum temperature. But
okay.
yeah.
Yeah, please.
No. Additionally, we can also use the LAOS. But so this is the typical approach that is used in the rheology to determine the maximum temperature.
Okay, excellent. Again, if you'd like to ask questions, just type them into the Q&A box located at the bottom or the top of your computer screen. We have plenty of time for questions, so please feel free to ask away at anything you'd like from the presentation. We'll move on here to another attendee question. Can LAOS be used to look at scorch or pre-cross-linking?
So I have not used for scorch. We use a different approach to detect the scorch with the RPA. So it's a very interesting question, but to be honest, we use a different approach.
Okay, so I guess, and we'll be talking later about asking questions specifically about applications right to the Alpha Technologies team. There'll be an email that will go out with information and with contact information to ask questions. So if there's something specifically that you want to talk about for test methods, use with scorch, for instance, Alpha should be able to answer your question specifically on that or anything else that you might have. So look for that after the webinar. Another question that came in, can you use the same LAOS technique for thermoplastics applications?
Yes, because it's also one of the case study that we, let's say, show in the presentation today. We showed that we were able to distinguish the macrostructure of a polyethylene that was completely linear and the one was long chain branched. So this technique allow to distinguish the macrostructure for thermoplastic materials. Yes.
Okay, so you can use it the same way for thermoplastics also.
Yeah.
Excellent. I'm not sure if you can answer this question or not, but I'll ask it anyway. Can I do the math by hand using older RPA models?
No, that'll not be possible unless you have the LAOS add-on. And this is because you need a sufficient signal-to-noise ratio, and you also need to be able to perform the harmonic analysis. So on the older model without LAOS add-on, it will not be possible to collect the different harmonics.
Yeah.
Okay, great. Can the technique be used to test stress hardening?
Maybe the question is about the strain hardening.
Strain hardening, maybe, yeah.
Strain hardening. So I think we can correlate the result or the outcomes from LAOS, so in terms of branching indexes with the strain hardening that was obtained, of course, by applying a different kinematic, different flow. We saw some study that showed that the LAOS probably show the same trends, but in terms of time, time is faster and is easier to produce deliver results. So it's possible to correlate the strain hardening with the LAOS or the long chain branching indexes. So some in several cases, the customer prefer to use LAOS in order to get faster the results.
Okay, so the speed of results, I guess, anyway, is the key.
So to
key
generate,
this.
To have faster the results.
Faster results, right?
Yeah.
Again, we have some time for questions, so if you want to ask one, again, Q&A icon located at the bottom or the top of your computer screen, and feel free to ask. Could you elaborate further on the onset of melt fracture and how LAOS can best attack that kind of branching? I think we're talking about in case study number 3, right? With that.
Yeah. So the melt fracture, let's say, was the processability issue that was should be let's say avoid. So we wanted to avoid the melt fracture, and the way to, let's say, to check if the material doesn't have any issue related to the melt fracture is to check with the LAOS with these long chain branching indexes values the branching content of the material. If the material doesn't have the proper branching content, probably we have problem related to the melt fracture.
Okay, excellent. How does LAOS work with the process? Can it help? Let's say you have an improved material that comes back with a quality issue. Can it help you determine what's going on with the process that you're doing with some of this too? I guess anyway.
So in this case, we have to specify which kind of process, because we have shown and described different type of application processes. We have to clarify more, we have to define better the type of application or process that we are talking.
Okay, so again, with that one, if there's more you want a specific process or what you're doing, it's better to talk one-on-one with the alpha expert, and they can walk you through some of that and talk about some of that. And I imagine that's something you guys do, is you can walk somebody through how to use the LAOS testing method and what's needed is specific applications, correct?
Absolutely. Yeah. So for example, if we go back to that melt or the melt fracture study, based off of the results you receive from that, you could then adjust your process using the information you acquired from the LAOS test method. So it is very application specific. If you're injection molding, extruding, whatever you're trying to do, that's all going to change. Temperatures, flow rates, shear rates, those all will have an effect on your processing. This is just a tool to give you some insights into your materials, so then you can optimize those.
Yeah, exactly. That makes sense. And another tool in your arsenal to use, along with, I guess, some other things that you mentioned at the beginning of the presentation too, that are available. Yeah, that's great. I know this is based on a study that you guys did too, right? That you can share with some of the elements of that too, I suppose, right?
Correct. Yeah, Michele actually wrote a paper for us that should be published shortly. So if you'd like to take a deeper dive into some of these case studies, specifically the gel case study, that paper will be released shortly.
Yeah, that sounds good. Well, that's all the questions we have for today. I want to thank everybody for attending this Rubber News webinar. and especially want to thank Alpha Technologies, Rick Hanslick, Michele Saki, and Unal for their attention to this and for the great work that they did putting together the study and some of that. Again, I want to mention, as I did before, that Alpha will be reaching out with an email to all the participants with more information. And if you want to get with them then to talk about specific applications, you can do that. At the same time, the presentation will be available. Okay, Rubber News site will be available to view within 48 hours of today's presentation. So you can go there if you want to see the presentation and review it again. So there's lots of ways you can look at it after the webinar today. That's it for today. Again, I want to thank everybody for attending. I want to thank our Rick and the two other Alpha experts for joining us today. And we'll see you at a future Rubber News webinar. Thank you.